Did you know that somewhere in our galaxy, right now, there exists an object so magnetically violent that standing on its surface, if such a thing were even possible, the magnetic field alone would tear apart every atom in your body before you got within 1,000 kilometers of it? That object is called a magnetar. And we're going to ask what happens when one collides with the most extreme gravitational entity in the known universe, a black hole. Now let's take a moment to appreciate what we're actually talking about here. A magnetar is a neutron star, the collapsed remnant of a star that once burned perhaps 20 times more massive than our sun. What's left behind after the supernova is a sphere roughly the size of a city, perhaps 20 kilometers across, yet containing more mass than the sun itself. Every teaspoon of its material weighs 1 billion tons. But what makes a magnetar different from an ordinary neutron star is its magnetic field. We're talking about a field 1,000 trillion times stronger than Earth's. Strong enough that it warps space. Strong enough that it can crack the star's own crust, releasing in a fraction of a second more energy than our sun emits in 250,000 years. These are called starquakes. And they are, without question, some of the most catastrophic events in the cosmos. Now place this object on a collision course with a black hole. Not just any black hole, let's say a stellar mass black hole, perhaps 10 to 20 times the mass of our sun. A collapsed region of space-time from which nothing, not even light, can escape. As the magnetar begins its inward spiral, drawn in by the black hole's gravitational pull, something extraordinary begins to happen. The tidal forces, the difference in gravitational pull across the width of the magnetar, begin to stretch and distort it. This process is called tidal disruption, and with a neutron star, it is not gentle. Unlike a gas cloud or even an ordinary star, a neutron star resists disruption far longer. It is held together by the most powerful nuclear forces in nature. But eventually, if the orbit brings it close enough, those forces lose. The magnetar begins to shred. Its outer layers are stripped away in ribbons of ultra-dense matter, spiraling into an accretion disk around the black hole. The magnetic field, that incomprehensible magnetic field, is now being compressed, twisted, and dragged along for the ride. What comes next is a release of energy almost beyond language. The collision would produce gravitational waves, ripples in the fabric of space-time itself, traveling outward at the speed of light in every direction. These are the same ripples we have already detected here on Earth, with instruments so sensitive they can measure a change in distance 1,000 times smaller than a proton. When two neutron stars merged in 2017, we heard it across 130 million light-years. This event would dwarf that. There may also be a short gamma-ray burst, a beam of pure energy, the most luminous explosions in the universe, launched from the poles of the collapsing system in the final moments before total merger. And then, silence. What remains is simply a more massive black hole, slightly heavier, slightly more warped, drifting on through the galaxy as if nothing had happened. But something extraordinary did happen. For a brief, blazing instant, two of the most extreme objects the universe has ever produced found each other across the void, and in their meeting, rewrote the space-time around them. We live in a universe that contains magnetars, that contains black holes, that allows them, given enough time and gravity, to find one another. And we, on this tiny, fragile world, have built instruments capable of listening when they do. That, to me, is one of the most remarkable things about being alive. If this filled you with wonder, subscribe and hit the bell, because there's so much more universe left to explore.